Hello everyone. In this video we will continue examining topic 5.2, the heating effect of electric currents, Ohm's law, and identifying ohmic and non-ohmic conductors. In the last video we finished up describing sort of what the graphs of current versus potential difference or potential difference versus current might look like for objects that obey Ohm's law, where Ohm's law again is equivalent to the statement that the resistance of a material is constant at all temperatures. Notice that delta V equals IR or V equals IR is not alone a statement of Ohm's law. It needs to be emphasized that R needs to be constant for it to obey Ohm's law. Delta V equals I times R, if R is not constant, is always true because that's just a rearrangement of the definition of resistance. So moving forward, there are actually many non-ohmic conductors that exist, including traditional lamp filaments, so light bulbs and incandescent lamps, what are known as semiconductor diodes, and we'll see what those are moving forward, and thermistors, among others. There are lots of different circuit elements that engage or are non-ohmic. So consider the lamp filament. That's our traditional, sort of most familiar example. Consider that what happens as the temperature of the filament heats up is that the particles and the materials in that very, very thin metal filament at high temperatures begin to move more. So they have higher kinetic energy, there's more internal energy, and so they are vibrating more and moving around more. And as a result, that resistance increases with temperature. Recall that this is sort of equivalent to trying to move across a crowded room where the difference is that, in a crowded room where nobody is moving quickly or nobody is moving around, it's a lot easier to get across the room, even if it's crowded, than if everybody is sort of bustling about and running into each other. So our question is, if a lamp filament's resistance increases with temperature, what should its delta V versus I and I versus delta V graphs be? I would suggest that right now you pause this video, and I'll give you sort of 10 seconds to do so, and make a quick sketch for yourself using these graphs where you predict what those graphs should look like. All right, so as delta V over I increases, the temperature will increase. So as delta V, not over I, but delta V or I increases, you crank up the potential difference and you crank up the current, the temperature of that filament will increase, and that means the resistance increases. And so a non-ohmic lamp will go from sort of having that first slope to having that second one. So let's consider these points. If this is delta V versus I, then a low resistance conductor will, for a given sort of value of delta V, be at a smaller resistance and therefore have a higher current, be farther along this axis. Whereas a point right here, okay, requires, more and more delta V to increase the current, okay? It's probably a little clearer, actually, with the independent and dependent variables on the correct axis. So for a given delta V, all right, you have a small amount of delta V, a small amount of potential difference or applied potential difference, you can get a pretty significant current. And there's low resistance there. But as that lamp filament heats up, it takes more and more delta V to increase by the same amount in the current. You can also get this by quickly flipping back and forth and noticing that the low resistance on the delta V versus I graph corresponds to that lower sort of sloped line right here, and higher resistance is on the higher sloped line, which means it's going to have this sort of shape. It'll go from a lower sloped line to a higher sloped line. One thing to be really careful of on problems like this, though, to find the value of the resistance, you do not take the slope. I know we have sort of trained you to do that. You're not actually finding the slope at these points. What you're doing is simply dividing the value of delta V over I right here to find the resistance, and dividing the value of delta V divided by I right here to find the current. It is not the slope of this line. All right. Then for a couple other sort of non-ohmic conductors, there are sort of different relationships. We'll talk about them more as we move forward. But in a thermistor, for example, which is a particular kind of circuit element, then at sufficiently high temperatures, a thermistor releases additional charge carriers. So additional electrons are released from inside the material, and that radically reduces the resistance as the temperature goes up. So this trend, you'll notice, is the opposite of a classic metal, as you might find in a lamp filament. Semiconducting diodes have the same general feature on this side, but they also have an additional feature, which is that current can only travel or go through the circuit element in one direction. And so they have sort of a pretty interesting I versus delta V graph. Delta V in the quote-unquote correct direction gives you a graph that looks a lot like the thermistor, and delta V in the other direction basically shuts down the current. As it so happens, you can actually break the diode by doing this. Diodes you might be familiar with. So this feature, the fact that it only goes in one direction, is related to the diode. This is a feature that is to be found in light-emitting diodes, otherwise known as LEDs. Note, a common misconception is that because the ohmic conductors are linear and the slope of an ohmic delta V versus I gives the resistance, the slope of a delta V versus I graph always gives the resistance. I've mentioned this before, but it's worth reiterating. R is equal to delta V over I at a point, not the change in delta V over the change in I, or dV dI. So be a little bit careful about this. Make sure that you're comfortable calculating R at a point simply by taking the value you read off one axis and dividing by the value you read off the other axis. So I'd recommend sort of taking a couple of points in these two graphs, actually calculating the resistance and observing how they will either be the same for an ohmic conductor or they might be different for a non-ohmic conductor.